Hello everyone, this is the presentation I gave last week in Turin, Italy at the 13th conference of the International Association for Applied Econometrics. My name is Angelo Milfont, I'm a PhD candidate at Pontifícia Universidade Católica do Rio de Janeiro, and my advisor is Professor Álvaro Veiga. Today I'll present our new article entitled Structural Breaks Detection and Variable Selection in Dynamic Linear Regression via the Iterative Fuse Lasso in High Dimension. Our main contribution is an efficient algorithm that can handle high-dimensional scenarios within practical time limits. I'm very proud to share our recent findings with you. Here's the path we'll follow in today's presentation. We'll start with our motivation to solve two critical problems in time series modeling. One, the detection of structural breakpoints, and two, variable selection from a large pool of candidates. We'll present our basic model and we'll go through a quick overview of the main challenges in high-dimensional statistics. Next, we'll talk about lasso, adaptive lasso and fuse lasso, three widely used techniques in machine learning, and look at how they can be extended to dynamic settings. Then we'll introduce a new extension of adaptive lasso that captures relationships between sequentially ordered variables. We call this new method the Iterative Fuse Lasso, or IFL. We'll run the fuse lasso through a three-step process. First, we identify structural breaks. Second, we simplify the model. And third, we select relevant variables. To assess the algorithm's performance, we compare it to the well-known path algorithm for generalized lasso. We carried out two experiments, one using simulated data and another with real-world data from an actively managed investment fund. We conclude by reflecting on our findings and outlining the opportunities ahead. Let's think about structural breaks. These are moments when something fundamental changes in the data, like a new government policy, a shift in the economy, or changes in how markets behave. Detecting breaks is very important because when we account for these shifts, we can end up with unbiased results, better forecasts, and better conclusions. Now let's add another layer, variable selection. When we have a lot of possible predictors, we need to figure out which ones actually matter. Choosing the right variables makes our models more accurate, easier to interpret, and faster to compute. It also helps avoid overfitting by cutting out the noise and focusing on what really drives the system. And now let's talk briefly about dynamic linear regression models, or DRMs. These models build on standard regression, but with a twist. They allow the regression coefficients to change over time. That's useful when you're working with time series data because in a real world, inflation, interest rates, or stock returns don't follow fixed patterns. They react to changing conditions. Static models cannot keep up with that, but DRMs can because they adapt. That's why they're so useful for forecasting and for spotting structural changes in the data. Our methodology builds on this idea. It offers a way to tackle these time series challenges almost simultaneously. We bet on sparse breaks and sparse relevant variables. We wish to model an observed time series using a large set of potential variables, plus some observational noise. We assume that the predictors are piecewise constant and the disturbances are IID with zero mean and constant variance. There's a small number of Q-relevant variables from a large pool of P candidates. The model is heavily degenerate with potentially one distinct beta at each time point. We'll soon show you that we have NP coefficients to estimate. These plots give a rough idea of the main concept. Our goal is to identify structural breaks in the predictors and select the relevant non-zero variables by estimating their values over time. We assume that there are just a few breaks in the relevant variables. Let's kick off our journey into high-dimensional statistics by talking about some of the main challenges we face. In high-dimensional settings, the number of variables, usually called P, is bigger than the number of observations, N, and that flips a lot of traditional methods on their heads. I'll soon show you that in our case, we'll have N observations and N times P candidate variables. Some of the core problems we face are Overfitting with so many variables is easy to fit noise instead of the actual signal we care about. Identifiability with more variables than data points. We cannot always estimate model parameters in a unique way. Multicollinearity. High-dimensional data often has variables that are strongly correlated. Variable selection becomes a real challenge. And there's computational complexity. High-dimensional problems can be very demanding in terms of time and resources. And these are just a few of the hurdles we face when working in high dimensions. Here are some key contributions that lay the foundation for our proposal today. In 1970, Hurrell introduced ridge regression, deliberately incorporating bias through a penalty term, stabilized coefficient estimates, and reduced the mean square error compared to the ordinary least squares. In 1996, Tibshirani proposed the lasso, a method that performs variable selection through regularization, resulting in sparse and interpretable models. In 2005, Tibshirani extended lasso through the fuse lasso, which encourages not only sparsity but also local smoothness among coefficients, especially valuable in ordered data like time series. In 2006, Zhu introduced the adaptive lasso, which adapts penalty weights to achieve consistent variable selection and attain the oracle properties. Most recently, in 2022, Ryan Tibshirani developed a highly efficient implementation of the generalized lasso dual-path algorithm, enabling scalable solutions to a broad class of regularized problems. Let me walk you through the basic ideas behind lasso, adaptive lasso, and the fuse lasso. Lasso, which stands for Least Absolute Shrinkage and Selection Operator, was a major breakthrough because it allows us to handle problems with a large number of variables efficiently. However, one limitation is that it doesn't have what we call the oracle properties. In simple terms, this means that as the sample size grows, Lasso might not always pick the right variables or estimate their effects, as well as if we already knew the true model. To address this, the adaptive lasso was introduced. It improves both variable selection and model accuracy by using data-driven weights in a penalty term, giving it the oracle properties we need. Then we have the fuse lasso, that not only selects variables but also encourages smooth changes in the coefficients over time, essentially working like a trend filter to capture gradual shifts or patterns. We now take the fuse lasso and the adaptive lasso and extend them into one dynamic formulation. This formulation allows us to detect structural breaks on its own, pick out relevant variables as things evolve, and still keeps the model stable and easy to understand. Now we're ready to dive into the iterative fuse lasso. Let's bring together everything we've talked so far to build an algorithm that can detect structural breaks and select variables in a fast and accurate way. The IFL works in three main steps. First, we detect the structural breaks, then we simplify the model, and finally, we select the relevant variables based on this simplified structure. To detect structural breaks, we start by reformulating the dynamic version of the fuse lasso into a static version of the standard ADA lasso. This setup allows us to leverage existing market standard routines to find a solution. To make this work, we reshape the design matrix X and the coefficient vector beta. The matrix X takes on a sawtooth structure and is now n times np. In this format, we can express the predictor vector as an np times 1 sequence of stacked betas, one for each observation and each feature. Next, we define L1, a matrix that helps manage the differences between consecutive observations feature by feature. Here, n represents the number of observations. Then we can define a new variable theta that captures the differences between adjacent betas. This is the key variable that solves our structural breaks problem using first differences. The new reparametrized model is y equals x times the inverse of L1 times theta plus epsilon. On the reparametrized model, we estimate initial thetas by ridge regression to use them as weights to the ADA lasso. And now we're able to run the ADA lasso to tune in the model and select the best penalty parameter lambda. We use the Bayesian information criterion. Whenever theta has a non-zero value, it means there's a meaningful change, or say a structural break at that point. Since ADA lasso naturally pushes irrelevant terms to zero and retains only the meaningful ones, applying it to the first different formulation leads to the automatic estimation of structural breaks in each feature. Now let's get into the smartest part of our process. Once we've identified the structural breaks, we simplify the model by collapsing repeated values together. This step helps us reduce the size of the predictors, making the model smaller and more efficient without losing any important information. To make this possible, we built an indicator matrix of zeros and ones, which we call M. This matrix links a reduced version of the predictor vector back to its original full length, so that B equals MBR. In a third and final step of our procedure, we run a new ADA lasso, but this time we use BR, the reduced version of the predictor vector that we built in a previous step. And our design matrix is now X times the indicator matrix M. We compute a ridge regression to find the initial weights of BR, and then we run the ADA lasso to estimate BR. To tune the model and select the best penalty parameter lambda, once again we use Bayesian information criterion. With the estimated BR, we can recover the full predictor vector B by pre-multiplying the mapping matrix M by BR hat. That is, B hat equals M times BR hat. This completes our process, which allows us to estimate the model's parameters in a clear and efficient way. To evaluate the effectiveness of the IFL approach, we benchmark its performance against the path algorithm for the generalized lasso, which is implemented in the GenLasso package in R. We carried out two distinct experiments, one using simulated data and another using real-world data. These examples demonstrate how useful the method can be in practice and highlight its potential in handling a wide range of high-dimensional scenarios. Our simulated experiments consisted of 18 sets, each containing 100 time series. In every scenario, we built a sample with 4 regimes, using distinct sets of design matrices to reflect different patterns. We varied 3 key factors across the experiments: the total number of features denoted by P, the number of truly relevant non-zero features denoted by Q, and the number of observations N. In all cases, we added observational noise that followed a normal distribution with a zero mean and constant variance. The goal of these simulations is to accurately detect the structural breaks in each of the Q relevant variables and to discard the remaining P minus Q irrelevant ones. We compare the performance of the IFL and GenLasso solution across all simulated scenarios using the Oracle solution as a benchmark. Our focus here is on how well each method identifies the correct number of relevant variables Q while fixing the total number of variables P and the number of observations N. The graphs we present illustrate the distribution of the bias in each of the 100 runs where we had N equals 120 observations. We analyzed 3 different scenarios. On the left, we have the case with Q equals 10 relevant variables. In the center, the case with Q equals 5, and on the right, the case with Q equals 2 relevant variables. In all of these cases, the total number of features is fixed at P equals 20. This comparison helps us understand how both methods behave as the variables become sparser. The challenge in the first scenario, shown on the left, is to detect structural breaks and correctly select 10 relevant variables out of 20. On the other hand, the scenario on the right, the task is to detect breaks and select 2 relevant variables from a group of 20. What we observe is that as the variables become sparser, the performance gap between the methods increase. The IFL consistently outperforms Lasso, getting much closer to the Oracle solution, which represents the best possible outcome had we had full knowledge of the true model. This suggests that IFL is particularly effective in high-dimensional settings where the true signal has sparse features. We now present results from another set of simulations. This time we use n equals 200 observations and consider the three scenarios with the same values of q equals 10, 5, and 2, while increasing the total number of variables p to 40. Once again, we observe that as the variables become sparser, the IFL continues to outperform Lasso, getting much closer to the Oracle solution. Finally, the tables report the average bias and mean squared error across all 18 scenarios tested. Two specific cases are highlighted, the sparsest one in blue and the least sparse in red. Overall, the tables show the IFL outperforms Lasso in sparser settings, confirming its advantage in high-dimensional scenarios. In a real-world case study, our goal was to detect changes and select relevant assets in a fund's portfolio. We built our portfolio using real financial data that consisted of P equals 20 daily stock return series from B3, Brazil's main exchange for equities and derivatives. There were Q equals 3 relevant assets at any given time, each active in specific periods, resulting in two distinct regimes. We analyzed a total of 758 observations covering the period from January 2, 2021 to December 23, 2023. N of IT is the total number of shares held of asset I at time t. Our objective is to estimate N of IT, which serves as our vector of predictors. Meanwhile, our design matrix is built from the returns of each asset. Each row of the matrix contains the daily returns for all assets at any given time. In a real-world application, both algorithms, IFL and Lasso, were able to successfully detect structural breaks in a number of shares held over time, select the relevant assets, and estimate their corresponding quantities in a portfolio. However, the IFL demonstrated a clear advantage. It achieved lower values of both bias and mean squared error compared to Lasso. Let's wrap up with a quick review of what we covered today. We introduced the iterative fuse lasso that effectively addresses the challenges of structural break detection and variable selection in high-dimensional time series analysis. Across all tests we performed, the IFL consistently detected the structural breaks and identified the key variables with accuracy. This makes it a practical and robust tool that can be applied to a wide range of fields dealing with complex and evolving data. This concludes my presentation. I thank you for your time. Please access the full article using the QR code on this slide.